Who likes using Symfony? Okay, a little less sense. So first and foremost, it's web applications, but it's composed of reusable components. So even if Symfony is not the framework of your choice, you might still be able to use the library that I'm talking about today. So imagine a web application that allows new users to register with this registration form. And remember, I'm a backend developer, so not a UI designer, so Twitter Bootstrap is the best that I come up with. So please forgive me about this. So if your users fill out this form, what do we expect to happen? And what do they expect to happen? So we expect that the account will be created and that the mail is being sent out and that the user can click a link on this mail to confirm their email address. And what about the user? This. They expect to see a page that tells them that they have done everything right and that the ball is in our field now and they need to wait for us to make the next step. So let's have a look at the workflow in detail. So first the user will submit the form, then we will validate the form, we will create the user account, we will send out this email, and eventually we will render this confirmation page that we just saw. So the first step is the action of the user, and the last step is the result that they expect. So which of the steps in between are actually mandatory to produce that result? So do we need to validate the form? Is this mandatory for this? Yeah, probably. If they've submitted an invalid form, then we want to notify them and tell them that they've done something wrong and should correct this error. What about creating a user account? Yeah, probably as well. So if the account couldn't be created, we probably should tell the user because they need to try again or contact the support or whatever. But what about sending this email? Is this actually mandatory to render this confirmation page? The problem with sending emails is that it's somewhat unreliable and error-prone. So what if it fails? We might retry after a couple of seconds or switch to a secondary email service. Maybe we use a library that already does that for us. The thing is, this takes time. And do we want to make the user wait? Also, if we fail to send that email, what is the user going to do with that information? They are a potential new customer of our service, and their first experience is that we failed to send them an email, right? Also, their account is somewhat in a limbo, right? It has been created, but the email hasn't been sent, so what's the user going to do? My hot take here is rendering that confirmation page does not depend on sending that email. So what if we could split it like this? After creating the user record, we immediately render the confirmation page, and some background process will tackle that email later. Next scenario. Let's say we have a shop that sells highly customizable products. Think about like cases, suitcases, toolboxes in some custom sizes where you can customize the size of the compartments and the color, and maybe you can have your product engraved or whatever. We give the customer an online tool where they can configure their product, and once an order has been placed, our customer again gets an email, of course, this time with an invoice attached, but because customers tend to have a bad memory, We also attach a PDF with preview images of their customized product and a detailed description of their order. Makes sense, right? Let's draw a nice workflow again. So user placed the order is inserted into the database, we render those preview images, we render this information document, we render the invoice, we assemble the email out of all of this and send it out, and we render the confirmation page telling the customer that the order has been placed. So again, which of the steps is mandatory to tell the customers that they've completed the order or successfully placed the order? And this is my take on this. Once the order is persisted in the database, we can confirm it to the customer. All the tasks that are potentially time-consuming can be done in the background. Like imagine rendering those images. This could take a while, right? And the PDF rendering. You probably don't want to do this like synchronously. This can be done in the background, and the customer probably won't mind if this confirmation email like arrives 10 minutes later or something. It's probably okay. Let's look at some code. This is how a Symfony controller for this example could look like. The order is persisted as a doctrine entity and passed to the individual steps, and we finally redirect to this confirmation page. And this big yellow block over there is the part that we want to move into the background. In order to do that, we introduce what we call a message bus. We dispatch the message that holds just enough information to complete this task. And since the order is persisted in the database already, a unique identifier that allows us to load the order from the database later on is sufficient for that. And at this point, we do not care who will process this order and how our message gets there. It's just that we declare that this task has to be done, and we want to just deliver it to someone who actually processes it. And this is actually the message bus's responsibility. It will take care of that. And on the other side of that bus, we need some kind of handler that receives the message we've just dispatched. All the logic that was previously in your controller is simply moved here. We fetch the order from the database and process it as we normally would. So you can probably imagine that we could also call this handler directly in our controller, and we would have the same result as before. It's just that the logic that we want to move in the background has been extracted into a separate class. So all we need now is something that fills the gap between the call to the message bus and this handler. And this is basically what Symfony Messenger does for us. Symfony Messenger provides a message bus with the ability to send messages and then either handle them immediately or send them through transports to be handled later. Coming back to our previous controller, again, you can imagine this message would be handled directly, nothing would have changed. It's still the same controller. But this is, of course, not why we introduced the bus. Maybe during development, or if you want to debug something, this is actually helpful, that you can see the synchronous message processing and you can see where something goes wrong. But in production, this is not what you want. The full power of the message bus is unleashed when a queue from the message and a background process that picks up the message is introduced. So the messenger itself does not provide a queue. It uses those transports, therefore, that I talked earlier about, and let's have a look at those. Depending on the needs of your application or what you already have, you might want to pick one of the transports that I'm showing you today. First of all, we have Doctrine dbar. This is probably how many of you have already implemented the queue without knowing it. The message is serialized simply into the database table and deleted from it once it has been processed. This might be enough, but the SQL database is not really built for this kind of access pattern of frequent insertions and deletions. Next is Redis. In many web applications, Redis is often used as caching backend or session storage, so you might already have it. It offers also basic functionality for message queuing, so you might get a queue without deploying a new infrastructure component. You can reuse what you already have to actually gain a message queue. Our third option is RabbitMQ. This piece of software is a dedicated message queue. This thing has been built for this kind of job. And it also offers some tooling and monitoring that you might find helpful if you operate a message queue. And then there's Amazon's simple queuing service, or just SQS. If you're deploying your application to AWS, then this service is already there for you, so you might just well use this. And of course, it does not end here. You can even implement your own transport if you feel like doing so. Maybe your favorite message queue is not supported yet, but you wanted to. Then build a transport, contribute it to Symfony, and yeah, this is how open source works, right? There's, for instance, open pull request for Kafka, but I think it's stalling. So if you can help with reviewing it, or with testing it, or if you can provide helpful input, then maybe we can help, or you can help getting it merged one day. So back to our application. These are the three places where our code actually gets in touch with the messenger component. We call the message bus via a really dead simple interface. So even if we are scared to introduce a new library because we don't want to couple ourselves too much with another library, this actually is not a strong coupling, right? It's an interface that you could easily re-implement yourself if you have a different queuing library that you want to use, right? And then we have this simple PHP object. It has no dependencies at all, has no reference to Symfony Messenger at all in there. It usually is just a plain PHP object with public read-only fields. So no logic in there, it just carries information from A to B. And last, we implement our message handler, which is a service that simply receives the message object that we've just built. And there's no reference to the messenger either, except for this small attribute on the top of there, which helps the messenger to discover all the available message handlers. But if you don't like this attribute, you could even do it without. It's just more configuration effort. So my point here is there is little reference to the messenger component here, and there's absolutely no reference to the actually queuing library or queuing backend that you're using. There's no code specific to RabbitMQ in there. There's no code specific to Redis in there. You could write this code and run it on whatever queue you like. You can even switch from synchronous to RabbitMQ or to Redis, whatever you have available in your environment. And this is actually one of the major design goals of Symfony Messenger. The code that you write should be as portable as possible. Let's have a look at the different actors of the Messenger component. We have a message handler that can handle one or multiple types of messages. So this is tailored specifically to a specific message class. We have a transport that delivers our message to the worker. We have the worker, which is what I previously called the background process. And this worker listens on one or multiple transports. And finally, the worker will call the message handler. And this is how we integrate all of this into the Symfony framework. Again, if you don't use the framework, you will just lose this nice configuration layer, but you can achieve the same programmatically. That won't fit on the slide, though, so I would kindly refer you to the documentation for that. First of all, we have the different transports here. Here we define 3: async, failed, and sync. They are configured via a DSN, which is basically a string that kind of looks like a URL. And we have the transport name fails, which is, for instance, just using our default Doctrine connection here. We have a sync transport, which will just dispatch the message synchronously. And finally, we have the async transport. And here we simply refer to an environment variable. And if you think about it, this makes sense. So probably the host name of your RabbitMQ server, for instance, will be different in your production environment and on your staging environment. Maybe in your development environment, you don't even use RabbitMQ, and you use the Doctrine transport instead. So you don't have to pin the actual transport in this configuration file. You can use an environment variable to switch the queue implementation that you're using. So let's again talk about this mysterious background process called the worker. The worker is a long-running PHP process that receives the messages, dispatches them to the message handlers, and monitors the success of the handling. And after a defined number of messages or seconds, it will shut itself down. The command up here is the simplest way to start the worker. In this case, it will just listen to all transports and will do so until it receives the signal to stop. But we can control the behavior a bit more fine-grained, as you can see on the right side. The worker that we configure there will stop after processing 100 messages, and it will stop after 1 hour. Depends on what comes first. And especially when we add a worker to an existing application that has never run outside a shared nothing request processing environment, our application might leak memory in the beginning. This is, of course, something we should work on. This is something we should monitor. But if our worker leaks memory in the beginning, we probably should lower those numbers a bit, because restarting the worker will heal this memory leak. Okay. And this worker here will process messages from 3 queues in that order. So that means that it will only process messages from my low prior queue if my high prior queue and my normal queue are empty already. While typing in that command might be feasible in your development environment, you probably don't want to do that in your production setup. Here you probably want to start multiple workers in order to process messages in parallel. Also, since your workers will regularly shut down, because we told them so, we need external tooling that restarts our workers, so it keeps them running. In a classic Linux server environment, you probably want to use supervisor D for that matter. If your application runs on containers already, you will want to create a dedicated container for your worker and tell Docker or Kubernetes how many copies of that container should it keep running. And please monitor your workers and your queue, especially memory consumption, CPU load, and queue size. This will give you insights on how frequently you need to restart your workers, how many of them you can run per machine, and of course, how many workers you actually need. And what happens if our message was not processed successfully? For instance, the handler threw an exception, right? We can tell the messenger to delay the message in that case and retry after a given period of time. But if the message keeps failing, this is where the failure queue comes in. This is a queue that is typically not meant to be processed. It collects all the messages that have been failed previously because we don't want them to be lost. They still contain information. For instance, that our user or our customer is still waiting for an order confirmation. We can also learn why a given message has failed by looking at the logged exception. Maybe it's a bug that can be solved easily, so we want to retry the message after a deployment, a bug fix deployment. Or maybe a microservice rendering or preview images was down or temporarily over capacity, so we might retry once this issue has been resolved. I've shown you a couple of features that the messenger provides. Now let's talk about what it cannot do for you. The messenger component is not a complete abstraction layer for message queues. There are aspects that are not covered, mainly because they could not be implemented in a portable manner, or because Messenger does not want to duplicate tooling that has been built around different message queues. The focus is really on having a portable solution for dispatching and receiving messages, and this is what you need most of the time. Of course, if you need that kind of functionality, you can implement this, but you will lose portability. So let's sum it up. A message bus allows us to execute logic asynchronously. Especially error-prone tasks or heavy lifting can be moved in the background this way. And Symfony Messenger hides the complexity of the message handling from your business logic. I thank you for your interest in this topic, and I'm open for your questions now.